So we'll skip heat for a bit now, and we'll go on to work done. So heat, I think you got a basic idea here as to what's happening. You're going to be having heat for a solid or a liquid. There is only one particular type of heat to be measured. Whereas when it comes to something like, what to say, a gas, you're going to be having two types of heat constants being applicable. One, which is going to be your specific heat capacity with respect to constant volume. Another is going to be at constant pressure.
Yes.
Okay. So now I'm going to move past heat for the time being here. Now, heat being this simple and efficient to measure was measured in large. Was it? By the way, is my what to say? Voice clear?
Yes, sir.
Okay. All right. So heat, because it is this simple and easy to measure, it was measured in large quantities. Basically, large amounts of it was measured. Huge amount of this data was actually available. So now let's come back to work done. Now, first off, physics, what all types of work done have you learned? What have you done in physics in thermo? What do you know in physics thermo? How many questions are you planning on skipping in thermo, by the way?
So there's only one question which will come. Long answer.
One question will show up, huh?
Yeah.
5 marker, huh?
7 marker. Yeah.
Huh?
7 marker.
7 marker.
Yeah. I mean, your choice though. So.
Okay, so you'll basically like completely chuck this guy out and you'll take something else.
Yeah.
7 marker.
Yeah.
That's like a large chunk out of like what comes now.
Yes, sir. But then they won't, even if you, they'll only consider one question, 2 questions out of the 3 they give.
Oh, 2 out of the 3 bits will be thermodynamics.
No. They'll give you 3 questions. One of them is thermodynamics. Other 2 I'm okay with. You can do any 2 of them.
Which topics?
Sir?
Other 2 are which topics?
Sir, SHM, oscillations, and this work per energy.
Yeah, easy enough. Huh?
Yeah.
Much easier.
Yeah.
If you're comfortable with mathematics, waves is easy. Work power energy is nothing that. Huh?
Yeah.
Thermo is the beast there, yeah. Okay. Now let's come to work done. So chemistry, when we are looking at the different types of processes. So when it comes to work done or heat, the idea here is we will start breaking it down into the different types of processes we have, and we'll start going into each of these in more detail. So I'm assuming you have a reasonable picture of the overall story we are going to be looking at in the chapter. I'm assuming part is clear now. So now we're going to look at each thing with a little bit more focused thing there. We'll start looking at each thing more closely. So first is Q and work done. Let's start off with the different processes possible. So what are the different processes applicable? You should have learned about the different types of processes.
Yeah.
List them down, please.
Isothermal process.
Isothermal.
Isobaric. Isochoric. Adiabatic.
Isochoric. Adiabatic.
Yeah, it's similar.
Any other names you know?
That's it.
Adiabatic process is also called as isoentropic process. Okay, now let's start off with each of these here. Isothermal. What is the mathematical condition here?
Temperature is constant.
Next, isobaric.
Pressure is constant. Then volume is constant. Heat is not, there's no heat. Delta Q.
This is basically what your 4 conditions are. Do you see what's happening here? What are these? What are we looking at here? I have a black box function.
Yeah. They're keeping something constant and studying.
Correct. Yeah. You're starting to recognize what is happening here.
Yes.
So in each case, that is basically what we are doing. The reason why our mathematical work is all aligned like this is purely because that is how they have to do shit to find shit out. So the way they started thinking was, I have a black box function. I want to study this guy. I will collect data about this guy.
Yeah.
When I collect data about this guy, I will try to collect data about this guy in such a way so that I can understand what are the variables this guy depends on. So I have decided this bugger is a function which depends on pressure, volume, temperature, number of moles, and heat.
Yeah.
This is work done.
Hmm.
You understand what I'm trying to explain here now?
Yes, sir.
Work done is my black box function here.
Yes.
When I see it is dependent on all of these things here. So what do I do first? I keep something constant. What do I keep constant? First,
Yes.
wrong. We keep number of moles a constant. We keep amount of gas a constant first.
Yeah.
Eliminate that guy out.
Okay. Yeah.
Okay. No, seriously, you have to start
Yeah.
thinking like them. You're studying a black box thing. You're studying some gas. You know some work is being done. You know that shit is dependent on each of these here.
Amount you keep constant, obviously. Yeah. Yes.
So now your job is to try to understand what that function is. So now let's start removing the variables which it depends on. First thing it depends on is number of moles.
Yeah.
Obviously. Throw that out.
Yeah.
Next.
You can go
So
to
there are
either
four
one.
variables now. All are
Yeah.
complicated variables.
Yes.
So one conditionality is you're going to be having heat as a completely separate thing. PVT are completely separate. So they started studying it at every one of these conditionalities. They kept everything constant. Each one of them constant. They started studying the work done. And they started seeing if there is something which relates them together or not. You understand the idea over here?
Yes.
So the principle here is initially when they were studying heat, they didn't understand internal energy, enthalpy, all of that. What did they know? They knew work done and heat are connected. So they studied these two in more detail and tried to connect them as much as they could. Only when they could not, remember, a bunch of scientists did this. And they all lost out on their way because they couldn't connect it meaningfully. They could connect work done and heat. They got the first law of thermodynamics out. They got some work done formulas, but they couldn't define entropy. They couldn't define interesting things. They couldn't really rebrand the subject itself. So those people got forgotten. They were the PhD scholars who wasted money, who became normal people. That is the unfortunate reality. PhD is that only. Coming back to the thing here. So black box function, work done. These are the four conditionalities, main four conditionalities. So let's start off. So I'm going to take my initial state and final state. So we're going to be looking at a particular gas in a box, standard gas in a box type of thing. So when you're going to be having a standard gas in a box type of thing over here, this gas in a box here, I'm going to consider the initial state S1 over here and the final state as S2 over here. Okay. So first, let's try to understand what is work done a little bit more closely over here before we go into anything here. Let's define work done here. Work done, I'm assuming your definition of work done for a gas in a box case is properly understood.
Yes.
Clear that?
Yeah.
Absolutely clear. I don't need to go into that.
No.
Okay. So work done works out as, in the case of physics, it will be P external into delta V.
Yeah.
In the case of chemistry, it is minus P external into delta V. It has to do with the sign convention.
On the system.
This is going to be work done in chemistry. We are going to be looking only from system point of view. On the system is positive, by the system is negative.
Yeah. Yes.
So on the system is positive now. If delta V is negative, this should come out positive.
Yeah.
So delta V is negative now, negative into negative, positive. That's
yes.
the So work done is going to be in this fashion defined over here. So let me just put the caveat here, work done on the system. It doesn't matter, work done, chemistry. Okay. Now, have we already discussed how work done is a path function?
No, sir.
We have not?
No.
Confirmed?
Yes, sir.
Okay, all right. Have we talked about how work done reversible? You sure we have not discussed how work done is a path function?
No, we didn't do that. So no.
Okay, all right. So okay, let's start off with the normal example I normally use for this. If you're familiar with the example, then I'll know whether we have done it or not. So let's say I'm going to be looking at, say, TVS XL and a bike. Have
Yeah.
you discussed any example involving them?
Yeah, we did. Oh,
So what the
oh,
hell?
that one. Oh, shit.
We have not discussed work done as a path function.
Yes, yes, we did. The dam thing. Yeah.
Yes,
Yeah.
that is work done as a path function, correct?
Yes, yes, yes. Yeah.
Think about
Correct.
how the process works. So let's look at the same thing mathematically now. So if
The
I'm
graph.
looking at it mathematically here, let's take the gas in the box case. Okay. So if I'm going to be taking a gas in a box here, okay, so let's call this as my state, final state S2. Okay.
Yeah. Yeah.
If I'm supposed to start off from an initial state S1, uh, so if I go from S1 to S2, if I'm drawing a graph here, so if I'm plotting, say, pressure, external, and volume V, how will this look? I'm starting from high pressure and
Low
end
pressure.
at low pressure.
Yeah.
Volume wise, low volume starting, ending wise, high volume.
Okay. Yes.
Correct? So I will have a sudden dip in pressure,
Yes.
and then I'll end up having increase in the volume happening.
Yeah.
Correct?
Hmm.
That's basically how it's expected to go.
Yes.
The graph is not perfect, unfortunately.
Yeah.
It looks a
Yeah.
little bit tilted. So let me redraw this a little bit more carefully. Suppose the axis itself is tilted, but shall we? Okay, correct. So let me tilt the axis out now. Give me a second.
Yeah.
Put this here, this done. Notability has all these perks.
Yeah.
Now, so in this particular case here, this is my initial state, which is of course going to be P1 V1. This is my final state, which is going to be P2 V2. All right, so state S1, P1 V1, state S2, P2 V2. Now I'm going to be having, let's say, a middle state coming into play here.
Yeah.
Now, if I have a middle state coming into play here, this middle state which is going to be here, I'm going to call this guy S3.
Yes, sir.
And let's say it's going to be P3 V3 here. What's going to be happening very simply is I will have an S3 in the middle here like this.
Yeah, between the two states.
So if I do have an S3 here, I will just have one more connection from here like this.
Then a dip.
I will have one connection going down like this from here,
And then again straight.
and one more straight path there. That's basically what it's going to be. So when you're going to be looking at this S3 here, this is of course going to be
P3, V3.
P3 V3 here. So we're going to be having in this particular scenario here, the work done in the first case is of course going to be this guy.
That area.
So it's area here. Whereas in the second case, it is going to be including this area here.
Yeah.
So that is the reality here. When you're going to be having work done, when you do it in more steps, it is going to be, you're able to extract more energy out of it. So this is basically the idea where we are going to be looking at work done being a path function. Of course, if I'm going to be doing it in infinite steps, what will happen? I can extract maximum energy out of it.
Yeah.
That's the basic idea here. Okay, now let's talk about some simple ways in which we can find out the work done here. First off, isothermal. Easiest one.
Yeah.
So not easiest actually. Isobaric is easier, but yeah.
Isobaric is easier. Yeah.
So isochoric is even easier.
Isochoric easier. You say.
Okay, huh. So isothermal is going to be delta T is going to be 0 here. So let's start off with understanding what is going to be this here. So I'm going to be having work done. Can simply be written as minus P external into delta V. Now in this particular case here, when you're going to be having isothermal process over here, what is the most interesting and important thing here? From first law of thermodynamics. I'm assuming you're familiar with what first law is.
Yes.
What is first law?
So D in this.
Conservation of fucking energy.
Yes.
Right? That's what first law is. Nothing else.
Yeah.
Don't call it anything else.
Yes, sir.
So I'm supplying some heat to a system.
Yeah.
Its temperature is not increasing. Why?
Yeah.
Because it is using up all the heat which I have given
Into work done.
do some work.
Yes.
So the idea here is its internal energy is not changing at all. Now,
Temperature is not
a couple
changing.
of important and interesting things. First off, internal energy and enthalpy. What are they a function of?
Temperature.
Good.
Yeah. Wait. Volume. No, sorry. No, pressure. My bad.
Volume and pressure don't come into the game here.
Sir, but then
The definition will have them in. H has U, H is going to be U plus PV and all of that
U
is
plus
correct.
PV, yeah.
But what is PV they are representing?
Work done.
No.
So,
Fuck no.
No, sorry. Yeah.
PV represents the amount of energy that molecules have invested into the space they are occupying.
Yes.
Do not call it work done at the beginning. Work done is a consequence of that.
Sir, can you repeat?
See, work done is a consequence of its space occupancy changing. Hence, we call it work done.
But here it's just saying.
If I'm looking at it plainly as it is, it doesn't depend on that.
Just energy. Okay. Yeah.
What does it depend on?
Number of moles.
Good. Why number of moles?
Because, kind of.
What are these two? U and H are basically energy variables, correct?
Yes. If you have more.
And temperature tells me what? Amount of energy I park into each account, correct? More or less.
Yes.
So I'm going to be having, technically speaking, U and H should be a function of T and S.
Yeah, S you can replace with. Okay.
But that S is going to be very complicated, right? That S is going to be total number of accounts actually, not the S which we thought of over there. The S over here, which we have to represent over here, has to mean total number of accounts.
Total number of accounts. Yeah.
Normally, we can't define that in a manner which is not per mole. So we'll define it per something and then we'll basically extrapolate it.
Okay. Okay.
So more or less, this is what it is going to be made up of here. If we have to get more specific, we can add a G over here as well.
Oh, yeah. Okay.
Now, but that is not going to be meaningful right now over here. So anyway, this is basically something unnecessary for now. But what is the idea here? What did I want to convey with this graph over here? So forget the S part. Okay, the S indicates that, think of it as phase is not changing. Why? Because if I'm having number of moles a constant, if I have number of moles a constant,
Yeah.
then technically this will not bother, then U and H will not be changing. Let's say I'm taking number of moles and temperature a constant.
Okay. Okay.
When will the S factor come into play?
When temperature is also playing. Sorry.
No, there's a phase change happening. When I have, say, 1 mole of water, liquid, changing into 1 mole of water gas, water vapor, at 100 degrees Celsius.
More number of accounts.
Number of moles is constant.
Yes.
Temperature is constant.
Yeah.
But internal energy and enthalpy are changing.
Oh, yeah. Correct. So it
Why
can
are-
independently also.
Because the number of accounts
Accounts are increasing. Yes.
mole is occupying is changing.
Yeah.
The molecules are gaining enormously larger amount of freedom now. So the molecules can park their energy into a lot more accounts.
Yeah.
So that factor, that multiplicative factor of change will come into play there.
So here PV will change.
So
H.
think of it like this. You got this part reasonably understood for now?
Yes, sir.
Now let me give a corollary for it. Then you'll understand it better. If no phase change,
This will not change.
we can think of U and H.
Simply functions of Tm.
Correct.
Hmm.
Function of only number of moles and temperature.
Okay.
So if I have both of them being a constant,
Then
what does it tell me about U and H?
they're dependent only on these two and the phase is same.
Correct. So now there is one more caveat here. This is not just phase change. I should have been a little bit more cleverer there.
Wait.
This is applicable for reaction.
Expansion. Oh.
What is phase change at the end of the day from this point of view?
Okay,
Something
expansion.
changed into something which had different level of freedom, correct?
Yeah.
So this shit is obviously applicable for reaction also. So if I'm going to be having no phase change or no reaction, does that sound fair now? No phase change, no reaction. If the same substance remains the same substance internally, in the same way it was present in the beginning, then my U and H are functions of only number of moles and temperature.
So, sir, by reaction, you just mean like the state won't change again, no? Like,
no, I'm talking about if there are, say, two substances present inside a box, both are gases. If those suckers react with each other, and one of them becomes, the product is going to be, say, one gas and one solid. That will change.
But then, in that case, what are you comparing? Like U and H, what are you comparing there?
U and H of system.
Intersystem. Okay. Oh, then that makes sense. Yeah. Okay.
Right?
Yes.
I'm looking at the entire reaction box of system, dude.
Yes, yeah, got it. Yeah.
Let me know when you want to end class.
Okay, sir.
And we'll shut whenever you feel like going about it.
Yeah.
Okay. So U and H are going to be functions of only temperature and number of moles. That means for an isothermal process, no phase change, no reaction.
Yeah. Well, then.
At delta T is equal to 0. What can I conclude?
It's only a function of. Oh.
Fair?
1 second.
Is this part clear now so far?
Sir, but wait 1 second.
For
Why
an
is it also?
isothermal process involving no phase change, no reaction, and delta N is also equal to 0.
Yeah, then that's okay.
I should have mentioned that. Sorry.
Yeah.
If I have all of these conditionalities, then I will be having at delta T equal to 0, I can say delta U equal to 0 and delta H is equal to 0.
Yeah.
Fair so far?
Yes.
Okay. Now, let's go for this isothermal process now. So in the isothermal process, you're going to be having delta T is equal to 0. So delta U works out as 0. Delta U, which is going to be nothing but Q plus work done. I'm assuming so far this part is not a complicated thing. You know first law, I suppose, yes?
Yes.
So delta U is going to be Q plus work done. You're familiar with this notation?
Yes.
In physics, you write it as Q minus work done.
Yeah, Q minus work done. Yeah.
Because the sign convention for work done alone is different. Everything else is same. Now, the meaning will come the same way, basically.
Yeah.
Okay. So delta U is working out as Q plus work done here, which basically means in this particular scenario here, you're going to be having if delta U is 0. Basically, we'll end up having Q being equal to minus of work done. Or rather, in physics, Q will be equal to work done. As simple as that. So Q is going to be minus of work done. Now, in this particular case here, Q is going to be, in this particular case here, minus of work done. Minus of work done can be written as minus P external into delta V.
Yeah.
Okay. So now in this particular case here, if I'm interested in calculating this work done here, I can do an integration and calculate it.
Yes,
The
yeah.
Q is much tougher to calculate in this case.
Okay.
See, think about it like this. There are cases where Q is easy to calculate. There are cases where Q is tougher to calculate. This is a case where Q is tougher to calculate. Why is Q tougher to calculate here?
Volume is like
Delta T is fucking 0. When will Q be easier to calculate?
oh, when there is a difference in temperature.
Then you can relate it to NS delta T or NC delta T or something of that sort.
Oh, I see. Okay.
Okay. So in
yes.
those conditionalities, Q is easier to calculate. In this conditionality, Q is tougher to calculate. So
Yeah.
if I'm looking at Q isothermal,
Tougher.
how I will calculate that is, or how scientists calculated that is, they calculated one.
Done. Yeah. Yes.
And they said this guy is that, so this should be that.
Yeah.
You understand how the game will start going from here?
Yes. Yeah.
So
Okay.
wherever I'm having a complicated variable to calculate, what will I try to do?
Try to find relation between
I
that.
will exactly.
Something you can calculate easily.
So I will link it up with something which is easier to calculate.
Or make new variables. Okay.
That is the game. You understand how this is supposed to work from here on out? So each time the way this works is you will basically end up wherever you are asked something to calculate.
So if that doesn't work, we would have to invent another variable. No?
You will have to find your way around.
But then when they couldn't do that, they invented new variables, right?
See, the idea here is this. If you have enough data available surrounding the graph, say, let's say I'm going to be looking at mapping out an area. Yeah. You're familiar with the Russia-Ukraine war?
Yes, sir.
Familiar to a decent extent?
Somewhat. A little.
So, you know how they got that Azovstal plant?
Sir, what?
You know, Ukraine had a plant called Azovstal steel plant.
Yes, yeah, there.
How did Russia get that?
They
didn't go in. They took everything around it.
Oh.
And they just slowly started squeezing it out.
Okay.
You understand the relationship over here, right?
Okay.
So the Now, let's come back to the thing we were discussing here. So the idea here is, when you're looking at a variable which you need to calculate, all you have to do is take the surroundings out.
Okay.
When you get the surroundings out, all the paths to the inside become clearer. So when the paths to the inside become clearer, inevitably you will end up there. See, for instance, in a question, let me. If you're solving a question, you're given infinite time. And you know it's a tough question, but doable by you. That's the key thing. You should feel it's doable by you. Only then you'll try. Otherwise, we will not even try. That's the problem with people like me and you. So if it's a tough question, but you feel it is doable by you, and you start off, you get stuck a little bit, but you still have confidence that it's doable. How would you proceed?
List out all the different approaches.
Huh?
List out all the different approaches. And you have all the time.
No, you'll calculate everything you can fucking calculate.
Exactly. Yeah,
Anything and everything you can calculate, you'll calculate.
exactly.
And then you put all of them up, and then you'll start seeing, "Arey, मैंने कुछ miss कर लिया कि नहीं?"
Correction. You can, yeah.
Ideally, that's what you'll go for.
Yes, sir.
See, somebody like you never gets pushed into that extreme. That's the truth of the situation as well. Because by the time, the problem is this, the arrogance which we develop through solving so many questions tells us that if we cannot do it in 3 minutes, it is not worth it to basically sit and plod over it. Or 5 minutes, it is not worth it. That is the thing which we have to beat down out of us. But anyway, that's besides the point. So the idea here is, abhi ke liye, if you are given a question of that sort, you identify all the things which you can identify with the data given, and then you will start approaching kya missing hai? How can I connect these data and get new data?
That's it. Yeah.
That'll be the next step, right?
Yes, sir.
So that's basically what these guys have done. They basically started connecting it and started getting new data. When they started connecting it, these were all the various connections they started finding. So you will be tested on all the various connections. Everywhere in which the connection is possible, you will get tested in each of those. Every one is like at least like 2 or 3 models of questions will come in each of those. So in this case here, Q isothermal is actually calculated using work done. How do you calculate that work done? You integrate the fucker and you get it. So you're going to be having dW being equal to, what to say, minus of minus aana chahiye. So this will become plus over here. So plus aa gaya hai, to Q isothermal is equal to minus dW, which will work out as plus P external into delta V into dV. P external here. Now assuming that in this particular case here, we are going to be having, see, this is an irreversible process, right? But if it is happening in an isothermal manner, what is going to be happening if it is happening isothermally? What does isothermal mean?
No change.
If I'm looking at it, what does isothermal mean? There is one more conditionality which I have not mentioned here.
Number of moles.
No, in this case here, I need to add one extra conditionality. Whether this was done reversibly or irreversibly.
8.
Because if it is done reversibly, what does that mean? That means we are having a path like this.
Yes.
We are having a nice clean path like that. That means my P external is constantly changing.
Yes.
Adjusting itself with the volume of that instant.
Yeah.
Correct. So if my P external is constantly changing, so if I'm looking at Q isothermal reversible, what will this work out as? This is my P external into dV. So let's integrate.
Into dV.
So integral of this P external is constantly changing and is related to my dV.
Yeah.
So I can write it as nRT by V.
Yes. dV.
Right?
Yeah.
Because it is constantly changing. If it is not changing, क्या होगा then? If it is not simply changing, if it is irreversible,
You can take P outside.
I can take.
P outside. It'll just be integral.
What does that mean?
It only depends on volume, the change in volume.
What does it mean then? Look at what I'm writing and tell me what's the goddamn answer for that.
Isobaric.
Hmm?
Isobaric case.
Excellent. Good, 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 good. Well done. So the P external, what is the value of this? Which value should it be?
Oh, that's what you mean. Oh, wait.
Check the graph here and tell me. State S1 to S2.
S1 to S2 then. This is P3. Oh, P2.
P2.
See. Oh, yeah. P2, yes.
So at that point, if it is an irreversible process, it is suddenly abruptly changing into P2V1, correct?
Yes, sir.
So if it is irreversible, it straight away becomes simply P2 into delta V.
Yeah.
Job done.
Sir, could you go to the graph once again?
Wait, let me finish this shit out.
Okay.
If it is work done irreversible isothermal, then this is going to be minus of P2 into delta V.
Yeah.
Okay, now what's your question?
So here we're assuming pressure to be suddenly dropped, right?
Yes.
Why can't volume be suddenly dropped?
Think. What am I able to control for my system?
Volume. Of this, sir, gas in a box. Yes.
Gas in a box. I am surroundings.
Yeah.
You understand? I am surroundings.
Hmm.
What can I change abruptly like this for the system? If I fart like this, am I getting the smell immediately?
No.
It takes some time now.
Yeah.
So is that an instantaneous change?
No.
Right. So now think that if it has to be an irreversible change, what can I change for the system? I can only change P external. I cannot change anything else.
So it just puts the piston
How do I
in.
change the volume? By changing P external.
Oh, you're saying we'll apply P external to push it in. Like,
Yes.
oh, that's. Wait.
How do I change volume for a system? By changing external pressure, by putting more pressure on it, or by reducing the pressure on it, I'll change the volume there, correct?
Correct. Okay.
Or I will increase the temperature for that. What does increasing temperature or decreasing temperature mean? Keeping the fellow in contact with something which is going to be giving it heat or reducing heat, correct?
Yes.
Right?
Yeah.
So that's basically what we're doing here. We can't change volume for the system.
Okay, fine.
Not as the first variable we have to change. You have to start understanding how change works. See, what is volume? Volume is something which will change when the molecules of the system go and hit against the other sides over there and then expand. Right? It is definitely going to take a little bit more time than changing the other variables.
Okay.
So pressure external is the easiest and the first thing which we can change. So in this particular case here, if I'm going to be having, say, Q irreversible, it is simply going to be P2 into delta V. Work done irreversible will become the minus of that minus P2 into delta V. If it is reversible though, what will it become? NRT by V dV, which I'm assuming you can do by yourself now properly.
Yeah. Yes.
Calculus is done for you guys to some extent.
So yes, sir. Yeah.
So NRT integral dV by V, what does this become?
Ln.
So ln V, what are my limits
V2.
over here? I'm having
From
V1 as my starting, V2 as the final.
Yes, sir.
So V1 to V2. So we'll end up having in this case here Q isothermal reversible will work out as
NRT ln V2 by V1.
ln of
V2 by V2.
V2 by V1.
Yeah.
Now, of course, we can write the same thing from the point of view of pressure as well,
P1 by P2.
in which case it works out as nRT
Non P1 by P2.
P1 by P2.
Yeah.
Now, if I have to put down work done in the same condition, constant temperature, reversible, this works out as what? This works out as exactly the minus of this. So minus of Q at constant temperature reversible, which is what we calculated in the first place. So it works out as the same thing, minus nRT ln of V2 by V1 or minus nRT ln of P1 by P2. Now, what should you do in terms of memorizing? See, there are some formulas to memorize. There are some you should not. This is up to you. This is up to you. Because depending on how weak your calculus is, that you will take some time to connect the pieces and do the calculus of it and get to this form, then yeah, memorize this shit. If your calculus is goddamn strong and all of this like aise aata tumhe connection, then you don't need to memorize this formula. This is not really worth memorizing at this stage. But you need to know the connection. You need to memorize the connections. You need to understand that in this case here, you do integration to get the thing. As long as you know that, you will solve it.
Yeah.
And you need to remember this is a reversible process. That is why the P external is connected to my dV.
Not good. Yeah. Yes.
Otherwise, it will not be connected to my volume at all.
Correct. Yeah.
So that is another key point to remember. And the last key point to remember here is that this is going to be involving isothermal. That means that Q has to be my work done because delta U is 0.
Yes. Yeah.
So you connect those pieces, you get your answer as you wish.
Hmm.
Now, ideally though, if you wish to get slightly faster, I would recommend you remember the formula.
Yeah. Okay.
Now, when I say remember the formula here, how should you remember the formula here? You should not remember all freaking 4 variations here.
Yeah.
You do that, you're going to mess it up. You
Yes.
remember only one, and then you connect it.
Hmm.
Okay, so this is for isothermal case here. Next, let's go for your isobaric. Isobaric. What is going to be happening here?
Irreversible. I mean, delta P is 0.
Delta P is 0. So what does that mean? In this
It's an
particular case,
irreversible
P
process.
external is P internal.
Yes.
Meaning we end up having in this particular case here work done.
Initial. That is. Yeah.
Whether it is irreversible or reversible, works out as what?
P delta V. Yeah.
P delta V. Minus P delta V.
Yes.
Okay. Yeah. Now in this case here, what will Q be? Q is at isobaric, constant pressure, right? So I'm going to represent it as QP.
Okay. Yeah.
How will I write this Q here? How will I find this Q here? That has to be found using delta U, correct?
Delta U.
Delta U is going to be Q plus work done. So in this case, work done pata hai. Easily mil jayega because this is easier to find here, correct?
Yes. Yeah.
Yes or no?
Yes.
This is easier to find here. So I can now calculate this work done a little bit more easily because it is minus P into delta V. The delta U is actually the more complicated one to calculate here, not QP. The QP here generally for this kind of a thing can be calculated quite easily as simply NCP into delta T. But people did not know this in the beginning. Can we clearly do?
Yes, sir.
So people did not know this properly in the beginning yet. This did not make clear-cut sense at that time. NCP, they did not know what CP meant at that time. They knew this, but they did not exactly know. So when you're going to be looking at this QP here, this is going to be something which will be delta U minus work done. So you can think of it as delta U plus P delta V. This is going to be your QP over here. Now, of course, this is effectively what changes into your delta H.
Oh,
Why? Because at constant pressure, what is H defined as? U plus
U
P.
plus PV. Yes.
So if I write delta H, I can write it as delta U plus delta of PV.
So we can say Q at constant pressure is nothing but delta H.
So this lead to delta H works out as delta U plus P delta V plus V delta P.
But V delta P is 0.
Correct. So at delta P equals 0 implies delta H simply becomes delta U plus P delta V, which is of course going to be your heat change at constant pressure. You understand the principle over here?
Yes, sir.
What did I tell you about heat change at constant pressure?
So,
This flow is a state function.
oh, that's, oh, yes.
You remember the point here?
Yes, sir. Yeah.
So the reason why I'm trying to connect the pieces now is, see, I gave you the story earlier. Now I'm going to connect the pieces.
Mathematically.
So you're going to be having delta H actually being a state function, mainly because it is related to the QP. Then. It is literally nothing but QP. It cannot be anything else but QP. Now, next. Let's go for isochoric. So if it is an isochoric process, what does that mean?
Delta V 0.
Perfect. So delta V is 0 now. We'll have what being 0?
Directly. Work done is 0.
Work done is 0. That means directly I will have delta U here.
Delta Q. Yes. QV. Yes.
Again, straightforward state function. Right? And you can write this state function as what? N into CV into delta T.
Yeah.
And what is my delta H being written as?
Delta H. Delta U plus delta
That
PV.
is true. What can I write it as? In this fashion. N into
NCP
CV into delta T.
Sorry, yes. Yeah. NCP delta T.
Correct. Now what do you see? You can see that internal energy is a function of what? Number of moles, temperature, and CV.
Volume.
Not volume, CV.
V is constant volume. Yeah.
Let's not consider it as CV really. We'll think about what CV is in a little bit of time. And lastly, what is H going to be?
Function of N, T, and then CP.
CP. So what is CV really going to be? What is this guy truly? Heat capacity for a particular mixture or a substance at constant volume, correct? What does that really mean? What does it depend on? We are trying to see dependencies now. I'm going to connect it back to the same shit I gave you in the beginning.
Also depends on temperature.
I gave you some crap in the beginning today, na? This crap. We are going to connect it back over here. Are you able to see my screen there a bit more?
Yes. Yeah.
Okay. So we are going to be connecting it back to this bit over here. How do we link it back? We have got the T part here, N part here. Now, the CV and the CP, they will change if I'm going to be having a phase change or a reaction happening.
Oh, I see.
You understand the idea here? So the CV or CP changes
State.
if phase change or reaction. So both of these will remain the same if there is no phase change or reaction. So my U and H are going to be remaining the same if there is no phase change or reaction, no temperature change, And finally, what else? No number of moles change.
Okay.
Clear so far?
Yes.
So now, lastly, let me give you the last puzzle. Now, we are not going to be solving this puzzle today. We're going to be solving this a little later. Now, when you're going to be having an adiabatic process, what is kept zero here?
Heat.
Heat is kept zero. So if I'm keeping heat as zero here, what happens here? I have delta U working out as work done adiabatic plus, of course, heat, but the heat is zero, right? So this bugger is zero. That means I will straight away have delta U for adiabatic.
Minus, say, plus.
For adiabatic is going to be work done adiabatic. Correct?
Yeah.
Now, is work done easy to calculate or tough to calculate?
Difficult.
Experimentally speaking.
Oh, work done is
Much tougher to calculate.
tougher. Yes.
Especially in something like an adiabatic, it is going to be a lot more complicated to calculate.
Yeah, it's fast. So
Now, if I'm going to be having something like this, how would I sit and get anything out here? Everything seems complicated here now. What is easiest to calculate normally for us?
heat.
What does heat mean? What are we? Why is heat easy to calculate?
Temperature difference.
You got to the correct point now. So let us now observe this adiabatic a little bit more closely. So state S1 linear is going to state S2. Okay. State S1 is going to be P1, V1, T1. State S2, I'm going to take it as P2, V2, T2. Okay. Number of moles, I keep a constant. Now, I want to find out work done adiabatic. Let's assume it's reversible. Reversible also works, but reversible or irreversible, let's actually first not make the question up. We'll keep it open. So, what is going to be the easiest way to calculate my work done here? Now, let me tell you what happens over here. Work done here is far more complicated to calculate, but delta U is a state function. This guy is a state function.
Yes.
So this fellow you can calculate in this fashion.
NCV.
Right? And then link it up to this book.
Oh.
So that will also work as a way to check if all of the shit which you have done is correct or not.
Sir, but then why would delta U adiabatic be equal to delta U and its constant volume?
Think. What is delta U?
Change in return.
So if I'm going to be having, say, state S1 being, say, P1, V1, T1, and number of moles N. Okay. If I have a theoretical state S3, okay, where I'm going to be having the pressure being P3, my volume is maintained as V1, and my temperature is finally become T2. Number of moles maintains the same.
Yeah.
Now, if I'm looking at delta U, let's call this as process 1. Process 1 is the guy in red. Process 2 is the guy in blue. Okay. Now, What is delta U for process 1?
Delta U.
Delta U for process 1 can be effectively written as work
Work
done
done.
divided. Correct?
Yes.
Delta U for process 1, it is internal energy, correct?
Yeah.
So it depends on temperature and number of moles.
Yes.
It doesn't matter what is the pressure, volume, and shit like that, correct?
Yeah, correct.
So I can say this delta U is going to be a function of the temperature and number of moles. Meaning it is going to be a function of the delta T involved here and the number of moles.
The second process is the same. Okay.
Now let's look at the second process here. In this second process here, I am going to be having the same delta U. Delta U in P2 is actually going to be the same as the delta U in P1. Excepting in this second process here, the delta U is going to be, instead of work done adiabatic here, this is not going to be something else. This is going to be an isochoric process.
Yeah.
So it will be heat change at constant volume.
Yeah.
You understand the idea here?
Mm-hmm.
Do you understand how we connect things over here?
Yes, sir. Got it. Got it. Yeah.
So the idea here is this is a completely theoretical step.
Yeah.
This is not really done at all.
Yeah, just to prove it. Yeah.
But the mathematics should work if delta U is properly a state function.
Yeah, we proved it is. Okay.
You understand the idea here, right?
Yes. Yeah.
So if delta U is working like a state function, this should be working.
Yeah.
All of this is based on that shit only, correct?
Yes, sir.
So if delta U is a clear-cut state function, my delta U in process 1 should be equal to delta U in process 2, which means my work done adiabatic there should be my QV in this second process.
Okay. Yeah.
समझ में रहा है कि क्या हो रहा है?
Yes, sir.
So now from there we'll be calculating the work done adiabatic. Now if I want to calculate the work done adiabatic, I will still be getting QV here, correct? So QV now I'll have to write it as NCV into T2 minus T1. Correct?
Yeah.
CV is what? For a gas, we will effectively be getting Cp by Cv being a new term called gamma. I'm assuming this is familiar for you?
Yes, sir. Yeah.
Now, so if Cp by Cv is this, another relationship between Cp and Cv is Cp minus Cv.
Yeah.
We'll derive this thing in the next session when we are discussing delta H and delta U link.
Yeah.
But I'm assuming this is familiar to you. So substituting that, you'll be getting Cv will work out as R by gamma minus 1. So you'll end up having this as N into R by gamma minus 1 into T2 minus T1. This is going to be your QV, or you can also call it as work done adiabatic.
Exactly. Yeah.
You understood the process here so far?
Yes, sir. Yeah.
We will talk a little bit more about this because this is not over. The game has only started. Because in questions where you have to calculate work done adiabatic, people are not going to be stupid and give you data directly. Adiabatic type, there are two types of things. In this case, you need temperature, T2 and T1. They will generally not give you this.
You have to find it through another.
Yes, ye milega nahi tumhe. If it is a reversible process, you can apply your adiabatic rules. PV power gamma equal to a constant and calculate your T2. You understand what I mean by that?
Okay.
We'll talk about that in the next session. Because much more complicated thing. We'll close here today. You have enough on your plate now. So in the next session, we'll continue on our work done journey and we will move into how to finish up the calculations for work done adiabatic.
Okay.
Good luck for your exam tomorrow, dude.
Yes, sir.
Do not screw it up.
Yeah.
I do not want blood on my hands unnecessarily.
Yes, sir.
so to say. Good luck. Do well.
Yes. Thank you.
Uh,
Sir. Yeah.
Any questions?
No, sir. I have not.
Okay, all right. I've
Sir,
confused
can
you.
you share the thing?